Hello, everyone. I'm very glad to be here to share the research we done in our lab about collective intelligence. So I'm very excited to share about everything I have done, but given 1 hour, I plan to give a broad brush of the different type of research we do in the lab. So hopefully this talk can spark some interest in future collaboration. So I'm assuming everyone in this room believes that human is the smartest intelligence on this planet. And I want to invite you all to think about what do you think can be smarter than a human? Yes, or a group of human. And of course, when it's not working, okay, a group of humans when they are carefully selected and coordinated. And a very classic example is juries deciding on a legal case. And in modern world, we have Wikipedia, where domain experts collectively added online encyclopedia. Whenever I think about it, I still think it's like unbelievably amazing. And I'm not sure if you have used Waze before to help you dodge speed traps. And it taps into the collective intelligence on the road, on the highway, for traffic hazards and accidents. And there's also citizen science, where regular people on the internet can collectively contribute to scientific discovery. And there's also Lego ideas where people can contribute design ideas about what kind of Lego toys should be designed next. So I want to invite you to play a game with me. So let's see if we're smarter together in this room. So here, I put some chocolate chips in a glass jar. And to make it easier for you to estimate, I give you two angles. One is on the side, one is on the top to estimate how many there are. So I put a QR code here. There's just one question. Please enter the number you think that best estimate the number of chocolate chips in the jar. And folks online, if you can fill out the survey, that would help with our collective intelligence here. It seems like folks in the room has submitted your answer. Let me see. Please don't change your answer already. All right, so here, let's see. Let's open the Excel sheet and quickly calculate your average. Here it is, so let's, okay.
No. I from both. That's mine. One from is 50, one is from 30. So it was 40 then. Two back to 40. The 50-30 one.
You're an outlier.
Yeah, no.
Do you know what to do outliers? We get rid of them. Go out.
Yeah, remove that one. Remove the 33. Yeah.
Okay, let's see. So the average we have in this room on maybe folks online is 75. And if you saw my slide just now, so the correct answer is I put 99. I promise I didn't lie. And I also asked 100 crowd workers on Amazon Mechanical Turk, and here is their estimate. So the x-axis are the numbers they submitted. So you could see similarly crazy number or crazier numbers comparing to what we submitted from 20 all the way to 1,000. And on the y-axis, I calculated how many people submitted those answers. So what do you think is the average of the crowd answer? It was 95, very close to the correct answer. And what is also impressive is the mode. So like the most number of crowd workers among all numbers selected 95, which is also very close to the correct answer. So here's collective intelligence for us. So this game represents a very classic concept of collective intelligence, like wisdom of crowds, which emphasize on independent contribution from large number of people, and it has a strong flavor of statistics. Like we are essentially averaging out those errors that individuals can make. But in modern world, collective intelligence is more and more facilitated by digital technologies, and it has been applied to a wide range of domains and research. So there's really no agreed upon definition of what collective intelligence is. But essentially, we're trying to elicit and synthesize individual knowledge into a group knowledge and to collectively solve some problems together. So today I wanted to share 3 threads of research we done in our lab on designing for collective intelligence. So the first thread is collective intelligence in the classroom. So the guiding question for us is, how do we design learning materials that are relatable to students from different backgrounds? And this work is funded by NSF, and I'm collaborating with Professor Ali Magana, Paul Thomas, and my student Vincent Zhou. So I'm sure we all believe in this room that teaching and learning is highly personal, and developing relatable examples to explain computing concepts has been a luxury. And here I want to share a personal story here. When I first learned about topological sorting as a junior student, my professor was using the textbook, this classic textbook of algorithms. And I was reading this example in the textbook that explained how topological sorting is important and how it works and how it applies to solve real world problems. And it tells me it can be used to sort a mechanical part, and each part can include instance of other parts. And I had no idea what that is. So I was technically learning about a new algorithm that solves a new problem, and I don't know either of those, what they are. And I was frustrated, but then I read the textbook more carefully. It says it's a practical application that is ubiquitous. So then if it is practical and ubiquitous and I don't know about it, it must be something wrong with me. Well, apparently it wasn't, but that was like a frustrating moment for me when I was learning computer science, although I overcome it eventually. And I don't blame my professor, because developing and tailoring those learning experience based on students' interest, background, skills are very, very difficult. It introduces a lot of burdens to the instructor. And also profiling learners can be very difficult. How do we measure academic and non-academic backgrounds? And how do we collect data to respect people's privacy and also make sure we have equitable data collection and training to have a fair profiling and accurate profiling of the learners? And how do we meaningfully contextualize the problem-solving scenarios into the student's background? So we want to be able to teach students to transfer their knowledge in new context, but the how well the problem is contextualized in those different scenarios will also be very important to make that work. So, for example, if we reframe a database problem about managing an inventory of electric parts into one about fruits, that doesn't really change anything. You're just changing the surface level of the names of those examples. So how do we deeply contextualize those problems into relatable scenarios for students? So coming from the background of collective intelligence and crowdsourcing, we propose to solve this problem or address this problem with the crowdsourcing paradigm, or when it's applied in a classroom, the learner sourcing paradigm. So learner sourcing is essentially applying the concept of crowdsourcing in the learning context. So there has been prior success of applying learner sourcing to support computing education. So prior research have used learner sourcing to collect student perspectives to overcome expert blind spot. So as instructors, when we teach, sometimes we forget how where novice struggle when learning about the concept, but we can tap into the collective intelligence of learners to contribute that insights. And researchers have also used learner sourcing to collect personalized hints to help novice learners when debugging their computer programs. Now, how can we use learner sourcing to co-create relatable problem-solving examples? So topological sorting can also be used for class scheduling and managing daily routine. So what got me when I was learning topological sorting is usually this type of algorithm requires some kind of prior knowledge about the dependency of the things that we are sorting. And the dependency itself is some sort of domain expertise that I needed to learn without knowing it beforehand. So what if the example tap into my prior knowledge? I already understand how the parts are dependent on each other, so I can focus on the new algorithm of topological sorting. So when we design learner sourcing, so first thing we wanted to contribute is how do we coordinate students in the classroom to be able to co-create that learning material? How do we scaffold them as with other crowdsourcing methods? How do we design a workflow that break down the complicated task into smaller, manageable pieces? So learner sourcing is not exactly crowdsourcing because it also cares about the learning. So we break it down into two sub-objectives. One is the learning objective and then the sourcing objective. So with the learning objective, it's this how students learn about the knowledge related to the class subject. So this is usually decided by the instructor, the learning objectives. And here the sourcing objective is how do we collect a relatable context? How do we contextualize the learning objective into that context? And how do we develop educational solutions that allow students to apply the knowledge in the class to the new context? And of course, as with other crowdsourcing workflow, we need to care about the quality control and calibration to make the student contributed content usable. So we use a database programming class as our test bed. So the class teaches advanced database programming concepts, and students in that class, it's usually junior or senior level, and they have already taken an intro level SQL course before they take this class. And since we're asking students to co-create learning materials and applying what they learned in class to a new context, we tap into the theoretical foundation of constructivist principles. And based on the principles, we developed initial design of the workflow. So the first component is activate prior knowledge. So this manifests the principle of engaging learners to actively seek new information. So this is where the learning workflow is integrated in the classroom. So if we want to help students practice one concept, then the workflow should be applied right after the students learn about the concept. And then the second component is contextualizing computing concepts. So this implements the principle of situating learning within authentic problem-solving context. So this is the difficult part, like identify the context and then developing a problem. Now, the third component is to create a worked-out example. The difference between a worked-out example and a regular example is it doesn't only describe a problem, it also provides the solution and break the solution down into step-by-step explanations. So this implements the principle of enabling students, enabling hands-on interaction with the task-related materials. And finally, we have a collaborative assessment where students will do self and peer assessment on the worked out example they created. And so this implements the concept of facilitating meaningful human interaction throughout the learning process. So we deployed this workflow and iteratively evaluated and improved it over multiple semesters in the class. And I will not bother you with the details of what we did in each semester and what we improved. But the guiding question when we worked on improving the workflow are how well did the student perform in connecting their own background to the computing subject, and how well did they formulate the contextualized problem, and how well did they develop the step-by-step solutions. And over the semesters, we identified a few challenges when the student try to contribute to this process. The first one is people don't always find it easy to ideate relatable and relevant context, because as the typical learning experience we have is I walk into the classroom and I wait for what the instructor asked me to do. And it's a new experience for the student to think about themselves when they're trying to fit in a new domain. And the second challenge is define relevant and clear problems. So sometimes students either struggle to articulate the problem they're trying to define, or they struggle to contextualize the concept into their scenarios. And the third one is providing dummy data, because the test bed we're using is a database class. And we will need some dummy data, some tables and structures for the queries to work. And generating dummy data has been a pain for a lot of students. And then, not surprisingly, breaking down the solutions into steps are like challenging, and also students sometimes complain about the learning benefit of some part of the workflow. For example, when it comes to evaluating other people's worked out example, some people thought it was more like them doing work for other students rather than them learning from the experience. And there is also a challenge from the instruction perspective. Like, so after we collect the student-generated content, of course, it is of mixed quality. So how do we pre-process and distribute the student-generated content to future students to make it more useful? So these are a few challenges we identified, and based on the experience of in-classroom deployment, we revised the learner sourcing workflow. So the first thing we did was we broke down each step into smaller sub-steps to provide some additional scaffolding to the students. So the way we activate prior knowledge was to both provide some traditional practices that the class already have about the learning subject, and we also provided a worked out example created by prior students or the instructor based on our personal experience. So I had a worked out example talking about desserts in Hong Kong, and also prior students worked out example also talked about their experience playing video games and other examples. So we provide example to the students of how worked out example can be contextualized in their own scenario. And then for the blue component here, we broke down the process of creating a worked out example into describe the problem background, formulating the problem statement, supply the related data, provide the solution, and then label the sub-goals in the solution. And then finally, we have the self-peer and instructor assessment. So we evaluate this revised workflow in the classroom across 3 assignments at different time of the semester on different topic. We collected the worked out example students created, their self-assessment and peer assessment, as well as the instructor assessments. So we define evaluation metric for different. A question? Oh, okay. So we're hearing ourselves. No worries. So we defined evaluation metric for different components of the worked out example, like how useful is the context, is the core subject meaningfully applied to solve the problem, and is the problem defined clearly so that somebody else can solve it, and the data quality, is the data usable to write queries, and the quality of the solution, the step-by-step solution explanation, the answer quality. So that's the actual code people submitted. And then there's also overall difficulty level and education level of the worked out examples. So here is the instructor's evaluation of the worked out example. We rated each criteria with a 7-step Likert scale. The green color means positive evaluation, and the students were doing pretty well, except that a small percentage of students create relatively simple questions that only require mechanical application of the concept in the class, and the education value, therefore, can sometimes be just moderate. So what is more interesting is the type of context we were able to gather from the students. So we have seen very exciting examples where students talked about their farm harvest at their grandma's place. And some of them talked about airplane engine parts that I'm going to stay away from. And some of them mentioned managing job application because we're dealing with junior and senior students. And some of them also talked about supporting local business during COVID-19. So they talked about Vienna, the local coffee shop at Purdue campus. So these are some great examples, but of course, some students struggled to still ideate a new context other than what I provided in the class. And students also sometimes struggle to describe the problem clearly so that others can understand and solve it. And providing dummy data remain to be difficult. And we'll come back to these challenges in a couple slides. So in addition to evaluating the sourcing outcomes, like what we sourced from the students, we also wanted to evaluate how well the student learned from the experience. So we measured there's ability to apply knowledge in new contexts using this adaptive expertise framework. So this framework has two dimensions, innovation and efficiency. So in this context, we define innovation as their ability to identify new context where the knowledge is applicable. And then we define efficiency as their ability to develop a solution to apply that knowledge in the context. So we measure innovation by how novel the contexts are, and then we measure the efficiency by the correctness of the solution they provided. So here we provide an example of how the students perform in one of the semesters across 3 homework. So homework 1 is early in the semester, homework 2 is in the middle of the semester, and homework 3 is later in the semester. And each homework is about a different topic as the course progresses. So overall, we see that more people go to the upper right corner, which means high innovation and high efficiency. But if we take a closer look, we realize the same students may move around in those 4 boxes. Like somebody, so for example, student number 11 was not performing well. It was on the upper left corner in the first homework, but they moved to the upper right corner quickly in homework 2 and 3. But some students were in the upper right corner, but then moved down to some of the lower corners. So we realized that although we were trying to solve personalized learning, we were facing personalized learning challenges again, that the different students may respond to this learner sourcing approach differently at different time of the semester on different subjects. So I worked with Professor Paul Thomas on double checking our assumption on how the context familiarity influences students' learning. So we were trying to get relatable context, but how relatable the context is only it can be decided only by the students themselves. So we reduced this concept of relatability to familiarity, and we checked whether what instructors intended to be familiar to the students were actually perceived as familiar, and not surprisingly, not always. So what instructors thought was familiar to the student, let me turn on the Okay, so what the instructor thought is familiar to the student is not always familiar. Like 1/3 of the students thought it was not familiar to them. And what the instructor thought was unfamiliar to the students, well, more than half of the students thought this context is actually familiar to us. And we also looked at how the perceived context familiarity influenced the students' confidence and course performance. And we realized that familiar context is more effective to onboard novice learners. But when they learn more about the concept, when they become more proficient, they like those unfamiliar contexts more because that brings additional challenge for them to apply the knowledge to an unfamiliar context. So overall, reflecting all the challenges that we encountered just designing the workflow, we realized there is a need for some additional scaffolding to the students to make the learning sourcing process, the learning benefit and the sourcing effectiveness work better. So we are now working on developing an AI-augmented learner sourcing system that address the challenges that we weren't able to address by purely improving the workflow design and the instruction design. So one challenge it allows us to solve is to pre-process and distribute a student-generated worked out example. We can have a backend system to algorithmically improve the quality of the worked out example and then assign students or allow students to choose a worked out example based on topics and subjects. And in addition to that, we also wanted to use AI to solve challenges such as communication clarity and generating dummy data. So these are the tasks like rewriting and improve the writing of their worked out example and defining dummy data is more for sourcing than learning. Students find it tedious and doesn't carry a lot of learning benefits. And also solution debugging. This is where personalized feedback would really help in real time, but given the limitation of the class, asking for TA's help usually require the students to go to the lab or send an email. So it's not really real time, but providing AI support would allow this help to be offered more timely. So This paper is submitted to IUI, it's under review. I just wanted to give you a quick overview of our idea of where AI can help during the learner sourcing process. So when it comes to designing problem context, the key challenge we're trying to address is the challenge in ideating relatable context. So previously, we would try to solve this by providing examples from previous students or the instructor. And here with AI, support, we can use both prior examples and AI-generated context based on the keywords the student provide. So they can provide a few keywords of their hobby, and then the AI can help them ideate the type of application scenarios of the course subjects. And the next step is writing out the problem background. And so here, a lot of writing support is needed, so AI can help proofreading and improving the clarity. And then when it comes to define the problem, it usually requires instructors to define a difficult enough problem that has education level. So here we hand it over to AI to generate a problem based on the course subjects and the provided context. And then the student can focus more on solving the problem rather than defining the problem. And also we handed off the data generation to AI, but student will take the role of evaluator of the AI generated content to evaluate whether the problem and the data satisfies or is applicable to the problem context where they are the expert for. And then when they develop the solution, AI will be helping as a debugger and evaluator of the solutions they developed. So that's about learning in the classroom. I think I'm running a little low on time. I do want to quickly talk a little bit about our work on collective intelligence for sensemaking. So this is, I want to talk more about the preliminary work than the work that we have done. So when I talk about sensemaking, the first question I usually get is, what is sensemaking? And so it's broadly defined. And here I wanted just to say it's about the process of making sense of information with a purpose. And usually sense-making includes information foraging and synthesizing. I'm not sure you have played the board game Clue for folks in the room. So they're like, it's like a mystery solving board game where you have evidence cards with people and location, and then you try to find out who is the murderer of the victim. And this is an example of sense making. We're trying to collect information and connect the dots. And what is also sense making is if you are a data security analyst and you're managing the data in our university and you need to decide which data needs to be protected how so that we fulfill the data protection policies. This is also sense making. And if you're a machine learning engineer, you're also making sense when you look at the training results and trying to decide what hyperparameter to tune and how. And I have done some work in supporting sense making in all the different scenarios, especially the first one, the mystery solving one. I try to use crowdsourcing to engage large number of people to solve a mystery together. But then LM comes. So all those work I did was before like LM become super powerful. And so I had existential crisis moment in 2021. Can LM solve those mysteries? And what is still to be solved with sense making? So I replicated the experiments I did with crowd workers, and I give the mysteries to the large language model. Back then, I was using ChatGPT-4. So in my crowdsourcing research, I had 3 mysteries of different difficulty level. The easy one is just 3 paragraphs. It's a riddle I found online. And the medium level mystery is a clue murder case a murder mystery that I generated with a clue board game. And the difficult mystery is from the intelligence analyst training material that has multiple coordinated terrorist attacks. So I threw my mysteries to LLM, and I found out that they solved it. So by solving it, I meant they got the correct answer. And that is where my existential crisis came in. I was like, okay, I'm glad I got my PhD before 2021. But I thought more about it. I realized, well, what does it mean to solve a mystery? Is it just the conclusion that we care about, or do we also care about the process, the analysis that goes from the fact to the hypothesis? And also, just by prompting the LM one more time or multiple times, I realized that analysis is not always replicable. So First time they got the correct answer. Second time I asked them to think again, they gave me a different answer. And so the analysis it provided also lacked detail and depth. So I took a closer look at the LM generated analysis, and I evaluated the analysis with two criteria. One is coverage. So with all the information I provided in the data set, how much information was covered in the analysis. And comprehensiveness is how much concrete facts were mentioned in the analysis. So for example, Scarlet killed Miss Bodie was the correct answer to one of my mysteries. But was the LM able to tell that the means, motive, and opportunity of this suspect from the data I provided to LLM? So I did a qualitative analysis and that where I calculated the number of facts and the number of hypotheses that LLM was able to generate based on the answer key. And here I also differentiated from concrete facts and like some like abstract ways of mentioning the information, but not exactly the way I provided. So I have some example here. So here on the left, I listed 3 facts. So Miss Scarlett was spotted at this address today at 10:50 a.m. This is a fact. And then this canoe hall is located at the same address I have here. And the third fact is there's a research talk here at 11 a.m. this Friday. Now, these are facts that the data I provided to LLM. And then the hypothesis that we as analysts can generate is, oh, Scarlett went to canoe hall. Well, we don't have fact for that. We just have this hypothesis based on fact 1 and 2. We can also generate a hypothesis that Scarlett went to the talk. This is based on facts 1 to 3, but we don't have hard evidence. These are only hypotheses based on the facts. And so that's how I differentiated the facts and hypotheses in the analysis. And you can see that, so sorry, it's not very readable. So the first bar in both chart is the step-by-step workflow. That's when I asked LLM to replicate the crowdsourcing workflow that I designed for crowd workers. The second bar is holistic. That's when I just dump the whole data set to LLM and say, solve this mystery, figure out who is the murderer, who are the terrorists, and what they're planning. And then the third bar is the baseline of crowd workers' performance. So we found that the crowd workers are much better at sticking to the facts with the mystery I provided, but LLMs are more like proficient in synthesizing the facts into hypotheses and provide some high-level summaries, although the summaries are not strictly tied to the facts. But that's the kind of rigor we want, especially when we are solving intelligence analysis mysteries. So I'm still thinking about what's next. So here are some open questions I'm thinking about. So with LLM in the loop, when we make sense in this world, how do we measure success? And what my prior research sort of tested the boundary of what crowdsourcing can achieve. What's the upper limit of what crowdsourcing can solve in terms of how difficult the mysteries are. But now that we have LLM, we have much more context window and computing capacity. So what's the boundary for LLM to solve mysteries? And how do we communicate and explain the LLM generated sense-making analysis to a different kind of human? So that's back to the success measure. So when we make sense, we want the human to be on board with all the analysis and evaluate the trust and contest the analysis we generate, and what are the risks and concerns with using LLM in the loop. Well, over reliance and trust and upscaling are all very valuable considerations. All right, so the third thread I wanted to discuss is how we prototype and evaluate human-AI interaction to support collective intelligence. So ultimately, I wanted to leverage collective intelligence to support collective intelligence. So when we design systems and interfaces for humans, we usually follow human-centered design principles, and it's increasingly important because now a lot of systems have AI feature embedded in it, and the impact on end users are bigger and harder to estimate for designers. So involving users in the design process is extremely important. However, there is always a communication challenge between the UX designers and the domain experts. So here I simplify the user-centered design process into 3 steps. So we need to learn about the context of use, specify the design goals, and then we iteratively develop the design solutions. And at each step, the researcher would need to talk to the users through interviews or surveys to try to gain that domain knowledge and try to communicate, and eventually try to communicate the design solution to verify if the understanding of the domain knowledge is correct and whether the design solution satisfy the design goal. So if you're familiar with the narrative writing technique, show, don't tell, right? So in this context, we have been telling all the time until we reach the design solution stage. So that's like maybe after multiple weeks and months of interview study. And I would say that's too late. And usually if you had experience with the user experience design, you would realize whenever you present the interactive prototype to your users, they will have a lot more new ideas than they used to have when you talk to them about their needs and design goals. So what if, now that we have vibe coding, what if we can accelerate the design process by incorporating the vibe coding technique into the design process? So on the left is what we typically do in the rapid prototyping. We start with sketches and then go from wireframe to mockup and then to interactive prototypes. And each arrow probably means multiple weeks. And what if we don't start from sketches? We ask generative AI to generate those working prototypes and use that as a communication channel between UX designers and the domain experts. So we tried this idea in one of our projects where we were designing a data interaction interface for highway traffic engineers. So the task here is the traffic engineers wants to have a better way of making sense of the traffic data they have. The traffic data we are using here is the 511 data. I'm not sure if you're familiar with it. So it's like 511 is a traffic system that collects data about construction, accidents, and also synthesize other traffic data, including weather, the sensors on the road. So it has a very rich data set from different perspectives about highway traffic. And this data is very complicated. When I first learned about this project, I was like, how complicated can it be, right? It's just constructions, it's just traffic accidents. Turns out they have like different event types, status, the geolocation, and then the different traffic events have different priority level, and they have also very granular information about the lane blockage, and the lane has positive, negative, and they have different code to describe the lane. And there's also shoulder blockage. There's very granular information about different types of traffic events. And there's also contextual information related to the road signs, the model name, and when the message is scheduled, and then when the message expire. There's also weather and CCTV data. So therefore, we needed to engage the traffic engineers to understand what they need and how they want to make sense of the data. And so we followed a typical design process. We first learned about the data, and LLM was really helpful in that process. And we also conducted needs finding interview to validate our understanding of the terminologies and the data set is accurate. And then we started to design the UI prototype to verify if we understand their needs correctly and if this is the good way of satisfying their goals. So we compared two design processes. One is a classic user-centered design. We have a design workshop. We sketched our design on the whiteboard like this, and we talked about different people's design and synthesized the design ideas, and then transformed that into low-fidelity prototypes on Figma. We also tried a different way, where as we were talking to the user, we are also talking to like the generative user interface tool. Like here we used Bolt. And as we were talking to the user, we were talking to the LLM to generate a user interface. And then once the user described their needs, and later in the conversation, we bring the interface to the user. Is that what you mean? Is this kind of a design good for solving the challenge you were describing? So within the same session, while we all remember what we were talking about, we were able to quickly bring some mock-up working interactive prototype to the user to support the communication between the UX designer and the end users. So this really helped us shorten the path between the user needs and the design prototype, and the design prototype and the user feedback. And this also was really helpful to upskill the UI UX designers and developers, because sometimes designers doesn't know how certain design ideas can be implemented, and sometimes developers did not think about the UI impact, the user impact of their implementation. But there's also a risk in converging too early on a design, because we're just showing a premature design to the user immediately. And another challenge is the generated user interface are not very editable. We usually need to go to the code to make any changes. Although there are solutions, I recently learned about Bubble and other tools that allows direct manipulation on the generated user interface, but it's not quickly enough. So this creates a lack of consistency and sometimes create confusion for the user. Like today you showed me one version of the app, tomorrow you showed me another version. What are we talking about the same design here? And then based on the risks in AI-generated code, so these are mostly used in our case for supporting the design ideation rather than the implementation stage. So how many times should I leave for Q&A? How many times should I leave for Q&A? Okay. So so the last thing I wanted to mention is, so we talked about designing human AI interaction early, and evaluating human AI design is also very challenging for the same reasons. So AI systems are non-deterministic, and the user contexts are also very different. So the model behavior are unpredictable, and then the communication logic that converts model behavior to system action is decided by the designers, and therefore can be different. And then for users from different background and in different usage context, the app can have all sorts of different behaviors. So when we apply user-centered design to design human AI interaction systems, the design principles can only support us how to convert the user requirement into design solutions. But when it comes to AI in the loop, how do we support the interface design for users when some of the features are powered by AI? So Microsoft proposed 18 guidelines for human AI interaction, and other big tech companies such as Google, IBM, and Amazon, Meta, they also provided a lot of guidelines. And we're using this one because this one is peer-reviewed academic research, and it synthesized more than 20 years of scholar research on designing interactive systems. So we evaluated how applying those guidelines can influence user experience, and what signals we can get to evaluate human AI interaction early, before the system is even developed and starting to impact end users at a large scale. So we conducted a factorial survey, and we looked at, for each given scenario, do people prefer a product that applies or violates the guideline, and what reasons they give for their preference, and what are the effects of applying or violating the guideline on different user experience metric. So here are some examples of the vignettes. So to make the study more consistent, we focused primarily on the productivity app. So we tell the user, hey, you are using a presentation app, just like PowerPoint or Google Slides, but it's a new app. And we give the app a new name so that they can contextualize the interaction in a fictional scenario. And then we measure different user experience metrics, including the feelings of control, adequacy, productivity, security, and certainty, trust, behavioral intent. So how likely would the user use an app that we described, and then the impact, and also the NPS measure. So how likely are you to recommend the product to a friend or colleague? So the study design implements two independent variables. So the first variable is the AI performance. So we consider the overall AI performance could confound with people's preference. So if the system perform well, do people always prefer the system? or does applying or violating the guideline also matters? So we have a 2x2 factorial design, and then therefore for each guideline, we developed 4 types of vignettes. Vignettes are just a textual description of the scenario. So we conducted 18 experiments for each of the guideline. That includes about 65 participants for each experiment. So overall, we had about 1,000 participants. So I wanted to give you a few examples of the results we have. Of course, like 18 experiments, that's a lot of results to cover. So for one of the guidelines, guideline 9, so that's the guideline that talk about when the system make a mistake, how the system should behave. So guideline 9 says it should make it easy to edit, refine, or recover when the AI system is wrong. So we implemented the guideline as a feature in the presentation app, so that when the presentation app suggests a layout, the user can change the suggested layout versus not being able to change it. So we found that people prefer being able to change the layout, and when people prefer the product that does not allow changing layout, it usually seems like a mistake. So sometimes prefer the product's name, and sometimes people explain that they like the application app, the product, but the selection was the opposite. So it's a mistake. And we also measure the user experience impact. So it seems like allowing user to make changes to AI suggestion has a very large impact on users' feeling of control and some other feelings such as productivity and feeling less certainty. So overall, we found a lot of positive experience for applying this guideline. Another example is guideline number 5. So this guideline talks about how the AI system should behave during the interaction. And it says we need to ensure the experience is delivered in the way that usually people would expect given their social and culture context. And we implement this guideline as how polite the suggestions are. And so here we say, oh, you are using a document editing app, and it's making suggestions to improve your writing style. And so the scenario for applying the guideline is, oh, you can consider using XYZ. And then the scenario of violating the guideline is the AI says you made a mistake, replace with XYZ. And to our surprise that sometimes people prefer a more blunt tone, because that way the AI sounds more confident and people would trust them more when the AI is more blunt and confident. And so we found like such individual nuances in terms of people's perception of how different implementation of the guidelines. And we also noticed that the effect size of applying or violating this guideline is relatively small. So sometimes, like for productivity apps, it might not be as important as, let's say, guideline 9 to provide control to the users. So overall, we try to contribute some evidence to support designers to choose or prioritize which guideline they should apply when they design a new human AI interaction systems, and which design patterns makes for better user experience. So what we did was just one way of implementing the guidelines, but there are so many different ways to make the system provide more control, to time the service, to provide global control, or to make clear what the system can do. So this type of vignette study can be a very useful method to prototype some early design of human-AI interaction before we go ahead and implement them. So we also did a follow-up study to look at the who in the UX impact, since we saw a lot of nuanced comments on, well, I prefer blunt behavior, although the intention of the designer is to fulfill the social norm, sometimes the design intentions are perceived differently. So we looked at how people with different problem-solving styles are influenced by the same human AI designs. So we used the GenderMag problem-solving styles. So there are 5 dimensions. There are attitudes towards risk, self-efficacy related to computers, and motivation, information processing style, and learning style. I don't have time to go through the details here, but we do found a lot of nuance in terms of how this problem-solving style can greatly influence people's perception of the same human interaction design. Although applying the guideline almost always lead to a more inclusive product design for the users of different problem-solving styles. But yeah, so I will probably stop here to allow some time for questions. So when I prepared for this talk, I didn't have time to have a complete list of acknowledgement to all the collaborators and my students, but I wanted to thank all my collaborators and students and my sponsors for supporting this research, and I hope to work with more people in our college in the future.
I have a question about when you use the ChatGPT. When you put those stories in it, are they your own news story or they are already exist online?
That's a question I get asked a lot. That's a good question. So now they're no longer new since I already provided the data. But before I send the data to LLM, I did try to prompt it to ask about the story I provided, and I don't think it used it for training. So the reason is, especially for the difficult mystery, that is like training material for intelligence analyst, and that was in a scanned PDF document that is like very difficult to be OCR'd. But now, I think I broke that rule. Yeah.
So then the next would be say, when you ask anything, think again. Typically, when we ask it again, we imply that your previous answer was wrong. So will that actually affect the LM to give
I think so. I also tried just to open a new window, like clear the conversation history and just replicate the prompt multiple times, and it does give me different answers. And I didn't include the results here, but we also try to set up a multi-agent team where we have different agents to handle each sense-making task. And yeah, when we run the experiment multiple times, the conclusions, the output they generate have a lot of variance.
At one point, there was a chain of thought, right? Because at least on the app, they can give you all the sequences, the why they come to each step. But
yeah, go ahead. Sorry.
No. So did you try that? I mean, do they have the same kind of the chain of reasoning and solve those things?
So the step-by-step prompt, I tried and I included here is sort of like the chain of thoughts. So the step-by-step prompt we generated is based on the crowdsourcing workflow we designed to guide crowd workers to solve the mystery. So we break down the sense-making task into 5 steps. And so that's sort of like the chain of thoughts, like to break down the overall prompt into stepwise instructions. And we found that constrained the LM performance. So, well, when I tried it, so it will focus more on the step output and it synthesized less in terms of the information it retrieves at each step. So I thought that was interesting. So overall, my experience is breaking it down for LM usually harm the performance. We are better off just throw the whole thing at it and it will figure something out. And maybe also when we talk about sense making, we use the model of sense making loop. So from the raw data all the way to the hypothesis. So what we have been talking about is the bottom up process from the data all the way to the conclusion. But one hypothesis I have is probably when we use LLM in our sense-making process, maybe the top-down approach would make more sense, where we use LLM to generate the initial analysis. And then as human, we probe why did you reach this conclusion? What are the supporting evidence to evaluate and then maybe attack or contest the LLM-generated analysis rather than like hand-holding it from the bottom-up process. Yeah.
I think this is a really interesting talk. One of the questions I had was thinking about at the very beginning that you asked us to play this game, right? Everybody had a different guess, and to take the average, you get much better results. Now, what about you have multiple AI agents instead of like right now we have like 30 people-ish. What if you have like 30,000 AI? Because with the way how you describe, the answers are often not consistent. But if you're using a similar kind of philosophy, can we get better results in this way?
So I tried asking ChatGPT, Gemini, and DeepSpeak with the same task. I didn't have time to repeat like 1,000 times, but when I asked them once, the simpler models performed better for some reason. But this is not replicable, of course. It's just anecdotal experience. But yeah, I would be curious to try how like it will work, because I'm like recently I'm also looking into like using LM to serve as persona of different kind of people.
Yeah.
And can we use LM agents to replace human in the crowdsourcing perspective? Yeah, that's a very interesting direction. I think we have only 3 minutes left.
I have a question.
No, I don't think so. It's pretty quiet. Folks online, do you have any questions for me?
I think the problem of using LLM models, you know, connectivity problem.
That's a good question. I should have included the sense-making model. I just didn't want to overwhelm people with the process. So, when I talk about sense-making, I don't think it's fundamentally different from reasoning. So when I talk about sense-making, I'm thinking about the process of like identifying some structure from the raw data. So sometimes we may have structured data like a table, but the data might not be structured in the way that we need to solve a specific problem. So for example, I might have a table of student grades and name and address, but I might not have the data is not structured in a way to help me understand which area is more popular for students. I need to like do additional clustering algorithm to answer that question. So the sense-making process I'm talking about is usually include 5 sub-steps. The first one is from all the raw data, you select the ones that are relevant to us. So if I want to ask students at Purdue University, then I will pick the only addresses within West Lafayette. And then the second step is to extract key information pieces. So you probably don't need all the information you have at hand. You will take the relevant ones. So you only need the address column and the student name column, for example. And in mystery solving, that usually includes, if I have a random news about Canoe building, but that's not related to the murder mystery we were solving, we're not going to include that in the later analysis. And then the third step is to schematize it. So when we solve mysteries, that usually include labeling the information. So if we're solving a murder case mystery, we need to label the means, motive, opportunity for each person. And then we use that to go to the fourth step to develop hypothesis. So Scarlett has means, motive, opportunity. And then maybe Mr. Plum only has means and motive. Or another person has also a means, motive, opportunity, but then we need to evaluate the plausibility of the evidence we have. And then finally, we reach a conclusion. We weigh all the hypotheses and to decide which hypothesis is more plausible. I don't think the process I talk about is very algorithmic in terms of reasoning. I don't know what kind of reasoning you're referring to, but I agree LLM cannot be used for reasoning. Yeah. Time is up. Thank you all.